Okay, so in this particular lecture, we're gonna talk about two particular things of Laplace transform. The first will be change of scale, and the second will be second shifting property. The first shifting property we have already studied under properties of Laplace transform. So these two things we are gonna study today. Okay. So we are starting with change of scale. So change of scale, this particular thing says basically that so if the Laplace of ft is equals to f bar s, that implies Laplace of f of at is equals to 1 over a f bar of s over a. This is what the change of scale property says. So we will now prove this. So how can we prove this? So basically see, let us first basically find the integration of this. So f of at equals to integration 0 to infinity e to the power minus st f of at dt. Okay, so substitute at with x, which gives you dt equals to dx over a, and t equals to x over a. So putting these values in the integration, we get Laplace of f of at is equals to integration 0 to infinity e to the power minus s upon a x, and this is fx dx over a, which is equals to 1 over a integration 0 to infinity e to the power minus s over ax fx dx, which is nothing but 1 over a f bar of s over a. See, here you have s over a. Clear? So this is the proof of the shifting property. Got it? Shifting property of Laplace transform. Let's take the next thing, that is the this was the change of scale property, not the shifting property. This was the change of scale property. Now we will be talking about the second shifting property, which is very important. With the help of this, we can relate two functions which are interdependent. Second shifting property says that, we will write in black only. So if the Laplace transform of f of t is given as f bar s, and there exists some gt, which is a piecewise function given by f of t minus a when t greater than equals to a, and is 0 when t is less than a, then the Laplace of gt is given as e to the power minus as f bar s. Clear? So basically you have some function ft whose Laplace transform is f bar s, and you have some gt which is given as f of t minus a when t is greater than equal to a, and 0 when t less than a. From there we can find the Laplace of gt, which is dependent upon f of t minus a basically. So L of gt, Laplace transform gt will be equals to e to the power minus as f bar s. So how can we prove this? Let's see. Proving this will be quite easy. So Laplace transform of g of t is equals to 0 to infinity integration e to the power minus st gt dt. So this can be separated into 0 to a e to the power minus st gt dt plus integration a to infinity e to the power minus st gt dt. This becomes 0 because gt is 0 in the interval 0 to a, and then this becomes a to infinity e to the power minus st. The value of gt in the interval a to infinity will be f of t minus a dt. Clear? Now we will substitute. So let x equals to t minus a. From here we get dx equals to dt, and t equals to x plus a. So putting these values in the integration, what do we get? So Laplace transform of gt equals, so when t equals to 0 x, so when t equals to a, x is 0, t equals to infinity, x will also be infinity. So from 0 to infinity e to the power minus s times x plus a, and this is fx dx. So this can be written as, so e to the power minus a can be taken outside, so e to the power minus as integration 0 to infinity e to the power minus sx fx dx. What is this? Nothing but f bar s, so e to the power minus as, this is f bar s. This was only our theorem to be proved, right? So Laplace transform of gt is e to the power minus as f bar s. Got it? So this is your second shifting property. Clear? These two things are clear, I guess. Okay, so this was all for this lecture, guys. In the next lecture we will be talking about some more topics. So meet you guys in the next lecture.